This is part 2 of the lesson on the design and implementation of the I2C driver module. In this part, we focus on the implementation and a demo. So here are the topics. We start by going through the IDE configuration for I2C and generating the startup code. Then we look at the overall software structure to see how the I2C module fits in. Next, we look at a few highlights of the module code and then the initialization code that was generated by the IDE. And finally, I'll show how this module is integrated into the module startup and superloop. Following that, we'll go through a demo where we'll look at a few use cases. We'll make use of the logic analyzer to see the bus activity on the wire. Finally, after a short summary, I'll provide some prompts or questions for you to try to answer. For each prompt, I'll give you a second to pause the video and then give you my take on the prompt. Here we are in the IDE, and I want to very briefly show you how I have I2C configured. Now, this configuration is mainly the default for the Nucleo board, except I have UART6 enabled here for reasons unrelated to this course. So regarding I2C, I chose to use I2C number 3 because I originally wanted you to use some specific pins. In the end, it didn't matter, but I just stuck with those pins. So I'll enable that I2C here. It's I2C3. Let's open it up. Enable it. Regarding the parameters, I just used the defaults, including the bit rate, which is 100 kilobits per second. Now, it chose these pins, but I wanted SDA to be on PB4, so I just do this, I2C3 SDA, and it moved it to pin 4. Notice it took it away from here. It also pinned it, which means if I were doing more work on this MCU, assigning other peripherals, it would not move that pin to something else, or that function. So then I want to make sure we're using the low-level library. And so I go to the Project Manager Advanced Settings, and here is I2C, I2C3, and it's not using low level, so we will change that. So I think we're good on the configuration. The last thing I want to do is generate the code. And there we go. And that has started. I'm going to pause here the video because this might take a little bit. Okay, so the code generation was successful, and so we're good to go with that code. This slide gives a complete overview of the structure of the software for the course project. This is to help you see how the I2C module fits in. By the way, this software structure was covered in detail in my previous base MCU course. So it's roughly in layers, and we'll start at the bottom with the system code and libraries, which are the gray boxes. First, we have the power-up code, which is the first instructions executed when power is applied, and the interrupt vector table, which controls which code is executed for the various interrupts. The power-up code does the bare minimum to provide an environment for normal C code to run. Next, we have the standard C libraries of libc and libm. As you may know, there are lightweight implementations of these libraries called newlib, and an even lighter weight version called newlib-nano. Finally, we have the C language runtime code, which is also very low-level stuff. It is closely tied to the compiler. Normally, you never think about this code, but I just included it for completeness. So now let's move up a level to the hardware access libraries, which are in these light brown boxes. These are mainly register-level access used by higher layers. There is the SEMSYS library, which is for the CPU and core peripherals like the interrupt controller, floating point unit, and so forth. And then there is the low-level library, or LL, which is for non-core peripherals like UARTs and the I2C interfaces. Now the next level up is IDE provided startup code, which is in this light green box. Some of this code is generated by the IDE and depends on which peripherals you have configured. Obviously, for our project, we have configured an I2C interface, among other stuff. So this code will initialize most of the hardware peripherals, except maybe for stuff that is done up in the modules. Now, all the software we've discussed so far has been provided by the IDE, including the toolchain. Now we move into code that I have written for this course and the base course. And this is the code that is in the GitHub repo. So first we have the module startup and superloop in this bright blue box. This code first just brings all these modules through 2 stages of initialization using standard APIs. Then it runs the superloop, which also invokes these modules or a subset of them through a standard API. Above that, we have a set of modules in bluish gray. These are the modules that use the SEMSYS or LL APIs, and thus are hardware dependent. So if we were to move this software to another MCU with different hardware, these modules would have to be modified. But their value is they provide a hardware independent interface to their users, and thus they provide hardware abstraction. We'll see how this works shortly. The I2C module is the one we'll be discussing in this lesson, so it has a red border to highlight it. At the top level are modules that are hardware independent. One way they achieve this is by making use of these lower modules that provide hardware abstraction. An example is this temp hum module, which stands for temperature humidity. It is highlighted with a red border since we'll be looking at it later in this course. It accesses a sensor that has an I2C interface, but it achieves MCU hardware independence by using the I2C module. If we were to move this module to another platform, another MCU, it should not have to be changed. So here's the code for the I2C module. There's a fair amount of code in here, although a lot of it is infrastructure stuff like console commands. I don't want to spend a lot of time looking at this code. I'm just going to give you a few highlights. And so the first thing is this enumeration for states. These are the states we actually looked at in that state diagram just a little bit ago. In that state diagram, I abbreviated them. But there they are. And then here is a key data structure in almost all drivers you'll see is, I call it state, which is a little bit confusing, but this is all of the data associated with a particular I2C instance. And so if we have multiple instances, there'll be multiple instances of this data structure. And it contains information like the configuration, a pointer to the peripheral registers, the I2C device, some information about the message buffer. This Boolean here indicates whether or not this instance has been reserved. Here's the actual state, and then we store some error information. So the next thing I want to show is just one of the APIs. This is a simple one called reserve. So here it is, I2C reserve. It takes an instance. It does some error checking, but if all goes well, it sets the reserved flag in that data structure to true, and now the instance is reserved. This reservation system is quite simple, and we'll talk about that in one of the prompts. So next I want to look at some interrupts, and let's go to 522. So this function here, this symbol, is in the interrupt vector table, and there is a default implementation for this that is just a tight loop. That default implementation, the symbol for it is weak, which means we can override it, which is what we're doing here. And there's quite a few of these for the different instances, and they all call a single interrupt handler here called I2C interrupt. So we can go to that, and you'll see we pass in the instance ID and the type of interrupt. So the purpose of the interrupt handler is to react to the event that just occurred, and which is essentially what a state machine does. And so a good portion of the state machine is in this interrupt handler. And this state machine implementation is what I would call informal, very informal. The way you can spot informal implementations is they often have a number of switch statements in them. In this case, we're switching on the state. More formal state machines will sometimes have tables of functions. And the nice thing about formal implementations is they are often better. They force you to consider every state, every event in every state um, to make sure you haven't missed something. And in these informal implementations, sometimes you sort of have to do that yourself and make sure you didn't miss anything. So, and because that can lead to state machines getting stuck and all sorts of things. So let's just look at this. We do a switch on the state. If we're in the right generating start condition, what we normally expect is the SB bit to be set in status register 1. And if that is true, it means the start condition was generated. And we now write the address and the read-write bit to the data register. And the state advances to write sending address. I'll mention here what's going on here. This is just my idea. I keep track in this variable which bits we have looked at or considered. And in this case, this says we have handled the SB bit. What that's used for is later in this interrupt handler, we check to make sure there aren't any other bits set that would be unexpected. In this case, based on this state. And if any of those other bits are set, that means something unusual is happening, and we have a very simple response to that. We end the transaction and we say it failed. Now, maybe in other drivers, you'd have to be a little bit more sophisticated than that. So this is, I hope, gives you a little flavor of what the code looks like, how the state machine is implemented, and if you're interested, you certainly could look at this in greater detail. You will see that there is a lot more complexity, a fair more complexity than that state machine diagram. The state machine diagram is accurate in the sense of it shows the transitions reasonably well, but there are a lot more things checked. And as I mentioned, those so-called special instructions add some complexity in some of these states. So here we are in the main.c file for our IDE project. And this is generated code. I want to show you the startup code for the I2C instance we're using. Now, in order for this code to be generated, we enabled the I2C device in the IDE. And we also specified that it should use the LL library in any generated code. So if we scroll down a little bit, we will find the main function right here. And scrolling down within that function, we see the initialization of the peripherals, and here is the function call for the I2C device, I2C number 3. And if I go to that function, we can look to see what it does. There's two main things it has to do. It has to set up the GPIO pins for the I2C interface, and then it has to set up the I2C peripheral itself. So regarding the GPIO pins, it enables the clock for the GPIO ports, and then it fills out these data structures, one for the SDA signal, one for the SCL signal. This is information about the GPIO pin, and then it calls this LL function, which takes this information and writes it into registers. Very straightforward function. So once the GPIO pins are set up, it works on the actual peripheral. It enables the clock for that peripheral. And then it does something, it sets a few things up. For instance, enabling clock stretching is one example. And then it does something similar as for GPIO. It fills out a data structure with all the information about the I2C device. Here happens to be the bit rate. And then it calls this LL function. And again, this LL function takes this information out of the structure and writes it into registers. And that's it. So it's not a lot of code. So this is the last code file we'll look at. It's called app_main, and it contains the module startup and the super loop. I just want to show you how the I2C module is integrated. So I'm going to jump directly to some lines. Here is the structure for the configuration structure for the I2C module. And then I am going to scroll down a little bit. And right here is where we get the default parameters for this I2C instance, and we store them in that structure. And then as soon as that happens, we call I2C init, which is the first phase of initialization. So I will scroll a little bit more. And of course, this is being done for lots of different modules. Here is the second stage of initialization called I2C start. And that's really it. Now here is the super loop. And if this module had a run function, we would be calling it in the super loop, but it doesn't. The I2C module works entirely based on interrupts. Now I want to do a few demos of this module. What I have here on the top of the screen is the logic analyzer program from Celia. It's called Logic. And I have a logic probe connected to this, as I showed in the first lesson. On the bottom of the screen, I have the MCU console, so I can enter commands. So I won't go through the setup of this logic analyzer in detail. I'll just show you what I have, or how I have configured it. So this shows the configuration of all the channels, or the probes. And I have one channel I named SDA, another one I named SCL, and the remaining 6 channels are all hidden. I'm sampling at 2 mega samples per second. There are faster sample rates, but I was having some problems. I'm not sure if it's problems with my laptop because I'm running a lot of software when I make these videos, or maybe it's a problem because I have a really cheap logic probe compared to the really nice ones from Celia. The other thing I would like to show you is I have a trigger set up. A trigger is something that'll start recording data. And I have the trigger defined. This means a falling edge on SDA. And if I can open this, a high condition on SCL. And that is the definition of a start condition. So that is a natural trigger. The other thing I want to show you is an analyzer. I have configured this to for I2C analysis, and when you set it to I2C, it'll ask you which channel is SDA, which channel is SCL. And this is some previous tests, so you don't have to look at that. We'll be looking at more of that in just a second. So first I would like to try a basic write and a read. I have a temperature sensor device connected to this, and it's at address 44. So the first thing we can do, well, let me show you first. There's an I2C test command, and if I enter it with no other parameters, it just gives me a list of all the different options. And you can see things like reserve, release, start a write, start a read, and so forth. So I happen to know what the command is to tell that device to start a measurement. And this is it. So we're going to do a write instance 0, I2C instance 0. There is only one instance in this software load. Here's the address of the device, and these are the 2 data bytes. And if I hit that, I got an error. I forgot to reserve the device. So let me do that. Reserve instance 0. And that succeeded. So now, oh, before I do the write, I forgot, I want to start the analyzer. So it will start looking for the start condition. And there it goes. It's looking. So now let's reissue the write. And we got a trigger. And you can see it, it would be on here, but it's off the screen right now. But we can look at the data, and we can see it's, there's a start, there was an address, 2 data bytes, and a stop. And here's what's really nice. If I click on this, it'll bring that to the center of the display. So here, let me just move this over a little. So here's the entire transaction. This T means this was the trigger point, and that also happens, that green dot is saying this is a start condition. Here is the address byte plus the read-write byte being written, and its act. And then here are the two data bytes, and they are act. And then this orange dot means that that means it's a stop condition. So we have given it the command. Now the next thing we want to do is read the result, and I'm just going to cut and paste that. I happen to know that this device, the result is contained in 6 bytes. So here, this command is going to do a read. Again, instance 0, address 44, and it wants to read 6 bytes. Let me start the analyzer. Make sure it's running. And I'll hit this, and we have that. And here are the data being read. Again, I will click on this to get to the beginning of the transaction. And this looks a lot like that write, except now it's a read instead of a write. And if I go over a little bit more, one thing I'll point out while I'm here is that it very conveniently labels the rising edge of the clock signal. And if you remember from the course on the theory of operation, that is when the SDA signal is sampled. And for whatever reason, for the ACK-NAC bit, it doesn't show that arrow. And I mean, that's fine. I think it sort of helps you find out which rising clock signal is for the ACK-NAC bit. But the main thing I want to show you here, back to the read, is that the last byte was NAC'd. And that's, if you remember, that's how reads work in I2C. So now I would like to show you, and let me just restart the analyzer. I would like to show you an error case. And so what we're going to do is try to read a non-existent address. So I'm going to do a test read instance 0 address, let's just say 11. I just some random value. And how many bytes? It doesn't really matter. I'll just say 2 bytes. And we got something. So let's look at that. And so here, same thing. Here's the start condition. We're trying to do a read, but in this case, it tells us the analyzer's figured out it was NAC'd. And we can look at that and convince ourselves it was NAC'd. This rising edge of the clock is where the ACK-NAC is sampled, and you can see the signal is high. If you remember, an ACK is low. So that address was NAC'd. What happened in the driver is it would have gotten an interrupt with an error bit set. I believe the error is called AF for address failure, and the driver would then generate a stop condition, and the transaction failed. And here, of course, is the stop transition. And I can actually use another one of the APIs called the get operation status. So we want to get the operation status for instance 0. And this first thing is a module error code, and -7 is defined as peripheral error. And that is sort of a generic status. And then you can then go to the module and say, give me the detailed error. And error number 6 would mean address failure. Again, if you looked at the header file for the I2C module. And the other thing I'd like to show is the general status command. And what it does is for every instance, it gives you just some of the information out of that state structure. This one here is saying that this module is reserved. Um, this is telling you some information about the last operation that was attempted, including errors and so forth. And also shows you what the base address is of that module. And then the other thing I'd like to show is the performance measurements. And these are generally error cases. Now this reserve fail, I'll tell you about that in just a second. The one I wanted to point out is it does show that there was one acknowledgement failure. This reservation failure is because there is another module running in this system. We're going to talk about it in the next lesson. And it's trying to also access this device. But since I reserved it, it is unable to reserve it. So it's constantly trying to reserve it, and it's failing each time. These PM counters are limited to, they're 16 bits, so this is the maximum value, so it's just sitting at that value. So that is a little demo of the module and the showing some of the console commands and showing the logic analyzer, which I hope you can see is very useful when you're trying to debug a problem. So here's a summary of this lesson. A minimal viable product for an I2C driver would support single master operation, 7-bit addressing, and simple reads and writes. The design of a module like I2C tends to be iterative and includes close reading of the datasheet or reference manual, making high-level design decisions, developing a state machine in many cases, coding and testing. A state machine can be used as the model for an I2C driver, where the states are typically the waiting points in an I2C bus transaction. Console test commands are handy for manual testing of I2C devices and inherently the driver itself. And a logic analyzer is very beneficial to see what is happening on the bus for debugging. Here are the prompts for this video lesson. I should mention that some of these prompts, especially the first one, require some analysis of the code. So I'll pause here for a few seconds in case you want to pause the video and look at these as a group. On the next set of slides, I'll go through the prompts one by one and reveal my take. What global or static variables, or I2C peripheral registers, if any, are modified both at the software base level and at the interrupt level? If there are any, what prevents simultaneous modifies and thus possible data corruption? Well, the I2C write and I2C read functions, which execute at the base level, call startop, and it modifies some fields in the I2C state structure and the I2C hardware registers. And these same fields and registers are modified in I2C interrupt or functions called by this interrupt handler. And some examples of the fields are in I2C state are message bytes transferred, last op error, and last op state. And examples of registers are control register 1 and control register 2. This isn't a problem because start op immediately returns if the module is not in the idle state. But when the module is in the idle state, I2C interrupts are disabled. So simultaneous modifies are not possible. Describe weaknesses of the guard timer implementation in this module and suggest possible improvements. Well, it's not too bad, but for the guard timer we have just a single timer with a single timeout value, and it's used to cover the entire I2C procedure. And this isn't optimal. For example, if there is a problem generating the start condition, we have to wait a much longer time before we report that error than we would have to. And that's because the timeout value has to be made to accommodate the longest possible I2C transaction. So the improvement would be that you could update the guard timer timeout period in each state to a value that is appropriate for that state. And this isn't uncommon in state machines. Often each state will have its own guard timer, and in some cases that guard timer might be quite small, other cases it would be longer. Describe weaknesses of the reservation scheme and suggest possible improvements. And by reservation scheme, I mean where you have to call I2C reserve before you can do an I2C read or write. So some weaknesses include it's based on the honor system. It depends on all users to play by the rules and properly reserving and releasing the I2C bus. As it works now, if user A has reserved the bus, then user B could skip the reservation and try to use the bus directly. The module only checks that someone has reserved it. Another issue is that if a user forgets to release the reservation, the I2C is locked out for all users, perhaps forever. And when I say forgets, what I really mean is that there's some bug in the user code, maybe some unusual scenario occurs, and the code does not release the bus. Finally, there is no method to ensure fairness. In other words, grant reservations in the order of the request. Basically, when the bus is freed, the first user to call I2C reserve gets it. So some possible improvements. One is when a reservation is granted, a unique reservation ID key could be provided by the I2C module to the user, and the user must pass that ID into APIs like I2C_read. And this key could just be a counter that's incremented for every reservation granted. Then the idea is the API functions would verify that the correct key is being used, or in other words, the most recent key. So only the user with that most recent key would be allowed access. For the second issue, when a reservation is requested, a maximum use time could be provided by the user, say 100 milliseconds. So the user is saying, I definitely will not need the bus more than 100 milliseconds. So then if the reservation is not released in that amount of time, the I2C module will automatically release it on its own. I don't have a suggested improvement for the third issue, but of course some kind of queue could be created to allow users to request a reservation and then be granted it in the order of the request, maybe using a callback function. The thing about all this stuff, you have to think about the purpose of the reservation scheme. Currently, it was just designed as a very simple way for users of the I2C module to perform their I2C operations one at a time and not interfere with each other. It was assumed everyone plays by the rules. So some of these ideas might be overkill, but some might be very useful and make the software more robust. It comes down to engineering judgment, and it could also come down to how I2C is being used in your application. This concludes the implementation and demo part of the I2C driver module. I hope it was helpful for you. And once again, thanks for watching.